spoke to Stephanie.
Pardon?
I dropped in unannounced. I'm going to wait until the rest of you have a few.
No, that's okay.
You can feel free to grab the phone.
Thank you.
Where are you from?
I'm from around
Which one
here.
is the veggie stuff?
Bottom two.
Huh?
The bottom two.
Bottom two, okay. This one has,
Chicken.
oh,
It has some veggie too.
oh, yeah. It's only veggie.
We had a professor in our undergrad.
That's very good.
And I had a classmate whose father had a chicken farm in India. So every time he went on vacation, this professor would say, Paresh Kumar, can you bring some veggie chicken? Like, what is that? Like, if you feed your chicken some vegetarian food, then it becomes veggie chicken, right? Used to joke, you know. I don't know how you will take that joke.
And what are the small pizza? It's like a specialized pizza.
Oh, chicken steak. That will offer, you know,
Okay.
pizza steak and bread steak, pizza and drink for $12. I just took that, so.
I should move.
Oh, let's see if it comes. Okay, there it is. Yeah.
You want some spicy stuff? I got some like chili pepper and all those things.
Okay. Yes, that time of the year. Okay, no signal. Let's put that. I hope it's very inputs. Nope, that's not what it is.
That's from you.
HMI1, let me see. Hopefully, I've done the.
So there is chicken and this one is veggie. The other one is just plain cheese.
Okay, so this one is cheese.
Veggie.
So veggies.
Just cheese and tomato.
Okay.
The other one is veggie.
Okay.
This one's chicken.
Okay. What is it? Oh, there it is. Okay, it's just, I think it's a loose connection or something like that.
Not to make white poly. I'm just the conduit. I wanted to make sure I had dinner. I'm not asking.
We hold it. Talking about this is race.
Okay. Yeah, as long as that's fine. I thought I think I would maybe look for a little more. That's fine. I would see. There's one. Yeah. Sorry.
Thank you. David said he won't be able to make it.
Oh, he won't be able to make it
Yeah,
today?
he has some event.
Okay. Okay, I thought he was, okay.
Yeah.
And that's fine. One of the things, I mean, I went across was like, we talked about the convolution last time, and this was like, what does that convolution actually see? I mean, we can cover that a little bit. One thing where I went to Karpathy's blog, this is from 2015, he talked about that. There are a lot of people talking about, and here's what in one layer, layer 3, either in a REST net or one of those nets, he's saying was, here's what 12 randomly chosen filters in a trained connet get excited about. And if you, these are the pictures he's giving it to it. And this is what it was getting excited about. These are what it was trying to see. And like, if he was giving a picture like this is what, each one is a different filter, 12 randomly. That's only 9.
So that's like on layer 3. Then later on, I will see more things.
Yeah, each layer sees a different thing. And then here's where the visual toolbox, this was the guy who kind of said, he developed a toolbox.
In this case, first layer, the unit in the center responds strongly.
Oh, it's not very visible. See, okay, we are having too much light. In fact, so he's saying is, this is what, if he gives he's going across con1, con2, you can go and see what it sees. And he's saying, if I give a dog, what does it see? And I was looking for a Medium article that talked about that. And each layer, what it was seeing.
Switch back and forth between showing the actual activations and showing images synthesized to produce information.
They are synthesizing images. These are the activations. That's where you're saying it's getting activated. And then they're somehow synthesizing an image.
We can further investigate this by showing a few different types of information. First, we can artificially create optimized images using new regularization techniques that are described in our paper. These synthetic images show that this neuron fires in response to the face and shoulders. We can also plot the images from the training set that activate this neuron most, as well as pixels from those images most responsible for activation. This feature responds to multiple faces in different locations. And by looking at the decon, we can see that it would respond more strongly if we had even darker eyes and rosier lips. We can also confirm that it cares about the head and shoulders, but ignores the arms and torso. We can even see that it fires to some extent for cat faces. Using backprop or decon, we can see that this unit depends most strongly on a couple units in the previous layer con4, and on about a dozen or so in con3. Now let's look at another neuron on the screen. So what's this unit doing? From the top 9 images, we might conclude that it fires for different types of clothing. But examining the synthetic images shows that it may be detecting not clothing per se, but wrinkles. In the live plot, we can see that it's activated by my shirt. And smoothing out half of my shirt causes that half of the activations to decrease. Finally, here's another interesting one. This one has learned to look for printed text in a variety of sizes, colors, and fonts. This is pretty cool because we've never asked the network to look for wrinkles or text or faces. The only labels we provided were at the very last layer. So the only reason the network learned features like text and faces in the middle was to support final decisions at that last layer. For example, the text detector may provide good evidence that a rectangle is in fact the book seen on image, and detecting many books next to each other might be a good way of detecting a bookcase, which was one of the categories we trained the net to recognize. In this video, we've shown some of the features of the GPU toolbox and a few of the things we've learned on YouTube. You can download the toolbox in this URL and explore for yourself. If you'd like to share what you find, you can use the
Okay. That was just, yeah, okay. And then there was another article I saw was, yeah, this is all, he's talking about selfies. Let me go back to this other article. I thought I had it in my Medium. No.
Were there more cups in the?
Out of these ones, that's all there was. There are some regular cups, like
Let me go
regular
to
ceramic cups.
trash, in trash. Auto hard coding concepts with real.
Downstairs? Sorry, the cups are downstairs. Oh.
Who's gonna make money?
This one, I can use it.
Just use that one.
You sure? Who's is this one?
That was here one.
Let me just go to this.
Sorry,
Was it here?
This don't need a lot of.
Let me. That's not it. And auto ML, that's not where that article was. Let me. Maybe I can search for Medium. This is a very old article. Visualizing. I thought I just saw something today. Probably no.
Yeah.
What'd you do?
He created his own data set.
To identify cricket batsmen and bowlers. The bowler is like pitcher. And
Which one?
He used one of his own data sets on the first model.
Yeah.
so I googled cricket batsmen and bowlers
Yeah.
and put
It's cool.
those to like the extension you sent to download those images.
Yeah.
Put those in folders.
Okay.
The model.
Of all the Indian cricketers?
Not Indian. Actually.
Yeah. Just cricketers.
Just
Well,
cricketers. Yeah.
top. How many different types of cricketers?
So many different types, but
Hmm.
bowlers and batsmen, those are the classes.
Oh, okay.
Pictures of batsmen
And bowlers.
pictures of
Oh,
bowlers.
okay. Yeah.
So
How many images?
around 250 for each. Each
Yeah.
class, yeah.
Yeah.
And got 81%.
Oh, okay.
Before fine tuning.
Hmm.
Didn't do fine tuning for that.
Okay.
Yeah.
So it should go up once you do some.
Yeah, it should go up.
Which notebook did you use? Did you use David's or?
So for this I used David's, but I did another.
80%. Did you? What else do you? Yeah. So the 80%. So did you do the LR finder, learning rate finder,
Yeah.
and then did that?
Yeah.
And what else have you? Then did you decrease the? Did you do any cosine annealing, or did you decrease the? Okay.
No differential.
Hmm.
Really. Just
Okay.
the basic model plus that layer.
Yeah.
To layer, then train it by LR5.
Yeah. Okay.
I guess the LR5 does not. It did not give me
Did he
the
give a result or
like the nice picture. I didn't get that
okay?
graph.
When I did
Here it goes. Hiromi.
data images, it didn't give me anything out because it's too small. He later on tells in the video that you need more than a certain number of images to
I see.
show anything on the graph. So it could be.
Okay.
I'm not sure.
Did you guys get this error on his notebook for lesson 1, David? Could the runtime error out of memory at PyTorch?
Yeah.
Oh.
That sometimes happens in Colab where people run out of memory.
No. Really? Okay.
So
But what kind of data set did you use? What do you use?
Well, I already got the data. I got about 400-ish of trees and
Okay.
bushes, shrubs.
Okay.
So, but I did not even try run. I'm just trying to run it with whatever David has in the cats and dogs.
Okay.
And I'm getting the error.
Hmm.
Do you remember
I think I got through it. I don't know.
You don't remember what you.
Let me look at mine.
I tried to start it and.
So, okay, so that's one thing before I get off. So you haven't decreased the learning rate and try to.
No, the thing is, when I did LR5,
Yeah.
it gives me this kind of graph.
That's fine. Sometimes it comes up like that.
Then I chose somewhere here.
Yeah.
Then did the training.
And then you can reduce the learning rate a little bit and see. And then there is that cosine annealing thing we can try. I mean, that's how you start getting it up higher and higher accuracy. Is, I mean, you try a few things and see if that'll improve it.
Right.
I mean, the other thing is also we can go back and start training a few more other layers, not just the fully connected layer. We can go and train layer. I have to see if it was layer 4 or layer 4 and layer 3, and we can open it up and start training that, and then that would increase the accuracy too. So, and you've used the Atom optimizer, I suppose. That's a good optimizer to use. So it's the learning rate, and then we got to cycle the learning rate. That's one thing you can try.
Right.
That has helped me a little bit. Sometimes it helps you a little bit, but if you're 80%, we don't know. I mean, where I was doing dogs and cats, it was already 98%, and you're trying to move 1% and stuff. So,
I tried all those things. The ones you have given in your notebook. For another data set.
Okay.
So that one was, so I didn't want to use good like 98% accuracy things. I wanted to give like hard problem for it.
Okay.
So what I did to identify Hollywood movie posters and Bollywood movie posters.
Okay.
To see if
it is able to distinguish between those two. Okay, that's a good. I mean, you can try that. Then the other thing to try is the transformations on the images. Yes. You can try a little bit different transformations and see if those things. I mean, maybe you want to rotate it a little bit or something. It depends on. Okay.
I turned off the flip.
The flip one.
I wanted it to turn the alphabet. Inside. The poster, but it didn't give me good results. Around like 70%, I guess.
Okay. Okay. We'll have to. I mean, I don't know if you want to. Where have you stored it in any place? It is accessible by other people, like an S3 bucket or something.
I've been pushing this to my GitHub.
GitHub itself. You stored it in GitHub.
Yeah.
Oh, okay. Okay.
But I didn't store the model.
Not the model, just the data itself. You stored the data. The data is what I don't think you can store that kind of. That's what I'm saying. If you, then other people can play around and see if they are able to get a better accuracy than what you've got. Yes. So that's the only thing to share the data. So if you can put it in an S3 bucket or something else, like Google Cloud
Google
Storage, yeah.
So I uploaded to Google Drive.
Yeah.
And mounted my drive to Colab. So
Yeah.
I can share that folder, my drive folder.
No, not your drive. Oh, okay. Your drive folder. The only thing is to transfer data from the drive folder. I've seen it takes a longer time compared to storing it in the Google storage. That's much quicker than Google Drive because, I mean, ultimately Google Storage is a payable product, but the Google Drive is not. I mean, I've just seen that it takes a longer time to download that thing. But Google Drive also, you can share that. I mean, it's not a whole lot of process, but it's still something. The thing is, you have to mount the drive and then do it and stuff. With the Google Storage, all you do is hit the HTTP location with wget, and you just get it. Otherwise, there is a multiple steps you have to go through and mount the drive, and then that's how. I don't know if we can even mount your drive. Probably not. That's what I'm saying. Sharing data becomes a problem if you're storing it in your drive and then getting it into Colab.
Yeah.
Then you'll have to download your thing from somewhere manually, somewhere else, and then upload it into Google Colab. So see if you can. I mean, Google Storage space is free. At least pretty much until 5 gigabytes or something like that. It's pretty much free, so you can store that data. So it'll be good to share data with others and stuff, and so people can play with it. So the CUDA thing, what you talked about, CUDA memory, what does it say? CUDA memory, I mean, we can search for it. That's something.
CUDA runtime error out of memory at PyTorch, atom source stage CT. .cu 25.
Oh yeah, okay.
Are you
Our
running
memory.
it locally, or do you have it running on a cluster of?
On Google Colab, yes, on GPU.
And GPU.
Yeah.
Runtime Google, yeah.
Because I've done this notebook, but I did mine a while back, and I got through it. But I didn't pull the more late.
But can you check if, I mean, you can say torch.cuda is available just to see is CUDA there? Torch.cuda is available. Like here, I mean, check CUDA is working just to make sure.
Okay.
This one. Yeah.
True, it's available.
Okay.
I can, you know what, I'll just run yours.
Yeah.
This way I don't have to
Run mine and
it's not
see.
here.
Yeah.
Because the reason I didn't try, because in the forum somewhere you said you should do it for lesson 1. The first area notebook doesn't work. Use David.
First will run out of memory and all of memory. It started warning about memory. And it may work. It started warning me about memory.
Yeah,
when I started doing that.
You said use David's. That's why I was.
Oh, okay. You can try mine too on that and see, and then post. I mean, if you get an error, just post it and I'll run it and see if there is what error it is.
Because I got all my images and all the folders set up already in S3 bucket. Yeah, so I followed all the directions and everything.
Yeah.
But I cannot run it because I can't get it
You try to reset starting the runtime and doing it again.
Yes,
Is that still the same error?
Okay.
Because I mean, yeah, I do get warnings sometimes, but if I do it again, sometimes I get errors.
But now, how much images are there? I mean, you can try. I mean, you can try reducing the batch size or something like that. But I don't know if that's going to help. But because how much batch size are you using? The standard 64 batch size or?
I just run his code.
Oh, his code is probably the default is 64, so that shouldn't be a problem. Okay, so try to run with mine and see what happens. If you don't, just post it on GitHub or something like that, and I'll get a notification and I'll try to run that thing and see what the problem is.
So you can just use the ones with B's and N's, and instead of B's and N's, just upload my files, right? So I'll change the code to
code to your thing. and then run it. So
okay, I don't have to do the other cats and dogs. I can do this.
yeah, Bayes and ants. Yeah, Bayes and ants is fine. So here is where in this article it was saying, hey, layer one. If you look at the layer one, that layer one only sees these kind of things here. The layer one. And I don't know exactly what, this is the layer two, which starts seeing certain things like this. What they're saying is, this is layer two. For these images, these are the activations they see in layer two. For these kind of images, because that convolution is going to see different images you put across, different activation is going to happen. And then in layer three, this article started at least had certain things. Okay, if they had this is what they saw in layer three. So they're not using the same images and showing the same thing for layer two and layer three and stuff to see, okay, this is what happened. And then what happened in layer three, they're just switching. I mean, there are different images they're using to show some of the activations.
So this is during each convolution? Or is it?
Yeah, this is the filter. This is each filter here. There are so many filters. And this, they are only showing these 9 filters here. Whereas there is a lot more filters than that.
Right. So when they say layer 1, do you think that's in the layer 1?
That's in the layer 1 of the network.
All of the hidden layers?
No, because you have remember ResNet and stuff has multiple layers.
Right.
And each layer has a connet.
Okay, so each time you run the connet, they're talking about those.
Yeah, they're saying, hey, this layer, when I'm doing this is what it gets activated here.
So the first time you run the connet, the second time.
No, this is a fully trained network.
Okay.
This is a fully trained network. And they're saying what are the activations they're seeing. In layer 4, they're kind of seeing certain things. So ultimately, when I read about this, I mean, whatever images you see in all these layer 4 and layer 5, you won't be as a human being able to identify, okay, this is what the computer is seeing as an image. It is seeing in some other fashion because it's trying to classify something. It's you won't be able to decipher exactly. You won't be able to see, if you showed it a dog, you won't be able to see the dog right there. I mean, you may be able to see some portions of the dog because this looks like the dog in layer 4. Yeah, layer 4 there. But as you get more and more in the higher layers, or the higher layers is where you start seeing the bigger, I mean, more close to the picture, more close to what it is. The actual objects you're wanting for. Because what they say is in these layers, it's trying to identify the edges and certain lines and all that stuff there. It's trying to learn more general things it's trying to learn, which is why when we do this, when we do the thing in the fully connected layer, I mean, we change we don't go and change the convolutional layer, but we could, as we said. I mean, when you're doing, that's why I'm saying, if you want to open up one of the last layer where it is actually seeing, you could get a higher accuracy because that's where it is seeing a lot of stuff. And then what we do in our thing, whatever we have been doing is we've not been opening up any of the convolution layers. It's all fully trained. We just only say, okay, we just changed the outcome here, the fully connected layer at the end, after all the layer 5. And then the fully connected layer comes in and we just say, you already know all kinds of images and stuff, which how do you fit that within these classes here? So all it does is changes the weights on the fully connected layer and stuff. But that's a start too. The fully connected layer is just a start. Okay, so that you can get that 80% accuracy right away. And then you start opening up, and then, but you don't, when you open up the other layers like layer 5 or layer 4, typically use 1/10 for layer 5, the learning rate, what you've used for the fully connected layer, and then 100 for the prior layer, because you don't want to change them too much. So if you started with 0.001 for the fully connected layer, you want to go 1e minus 4 for the convolution, 1 layer above and 1e minus 5 above that. So you only want to change a little bit there, so that to try to improve the accuracy.
So when you do LR find,
yeah, LR find is only
It gives you like average kind of learning rate.
Yeah, it gives you an average kind of learning rate. If you had opened it up, all it does is it applies. Well, let me take it back. LR find and fast AI, what it does is it'll ratio it off as you specify the different learning rates. So if you look at his thing, I'll show you what he means by that. Let's go here on his GitHub. Here, I don't think it courses lesson 1. Yeah, this is all first thing. He does all the stuff, and then what he does is choosing a learning rate. He does that. He does the plot. Does all that. He gets into pre-compute. This is just a scheduling unfreeze. Here's where he's unfreezing. See, he gives a learning rate, an NP array of this. So what it does is our fully connected layer, we'll leave it at 1e minus 2. The prior layer, he does 1e minus 3, and then the 1e minus 4 to the other layer. And then when he does any of the LR find, it'll keep these ratios the same. It'll keep increasing it at that rate. It won't change all the, so what it'll do is it'll start at 1e minus 5 on the, usually he goes, when I looked at his LR find, it goes from 1e minus 5 to 1 or 10. I think 10 is the max. So when he does that, so 1e minus 5 means it'll go 1/10 and 1/100th of that for the other layers he's opened. So it does that, but when I looked at the code, that's what it does. So it always keeps that ratio. So when you do the LR find, when you open up some of the layers, it'll still keep that ratio and say, what is that, the learning rate you should use for the fully connected layer.
So basically what we use is the learning rate of the last layer.
Last layer. It's using, yeah, it's only showing you the learning rate of the last layer. But internally, it is not going to apply the learning rate. It only applies it at this array, whatever it takes that array and applies that in the learning rate find. But yeah, the learning rate find is a great tool. I mean, I've seen that. I mean, when I was doing some of the work this weekend on the columnar data set, it helps quite a bit. I mean, because there is no pre-trained network or anything. You're starting from scratch. And you want to know, okay, what is it? Because if you start with it completely goes away to some different place. If you use a suboptimal learning rate, if you use too high learning rate, it just goes away somewhere. And then it's very hard to, again, bring it back. So you want to use the learning rate finder before you start actually training the network and see what kind of optimal learning rate. And that kind of then after a few epochs, like 3 or 4 epochs, then I'll do the learning rate finder again. And see, okay, am I still in that range? Should I reduce it, or am I okay kind of in that? But I'm still finding, I mean, that learning rate thing is kind of powerful when you get into, like the cats and dogs, you don't see it because it's a 98, 99% accuracy. You don't see the effect of that. But you see these cosine annealing where he cycles the learning rate, and the learning rate finder and stuff. When you're getting into this 80% range and stuff, you can shift the accuracy by playing around with the learning rate. And so that was, yeah. And then, yeah, both me and he has the thing called the testing time augmentation. That also, he says, improves his prediction. All he does is he does an ensemble of predictions. So he does different transformation of the test set itself and then makes prediction using those transforms and then averaging it out the predictions.
Yeah, I noticed I got a big boost after that.
Yeah, the TTA. Yeah, the TTA helps quite a bit because he's saying I've trained the network, but when I'm predicting it, I'm just not going to, I'm going to transform the images, but I'm going to do 5 different transforms. I don't know which transform works well. So I'm going to do 4 or 5 different transforms. and I'm going to take the average of the result. And he gets a boost in this thing, boost in the accuracy. Again, you won't see it that much in the dogs and cats because you're talking about 99.1 and stuff. You don't see that needle moving. I mean, even a 0.1 here is a big deal when you're that accurate there. So going back to this thing, I mean,
So it should be able to predict correctly for
the sportsman. I mean, when you're saying bowler and batsman, it has to know if there is any. I mean, it can be just a face. Because how is it going to? Because you give them the. I mean. Either the person has to have a bat or a ball. Something is able to distinguish between a batsman and a bowler. Because how else will it be able to tell this is a batsman and this is a bowler?
There's so many other things you can look at.
Oh, yeah. Yeah, make it harder. I mean, you have to...
Yeah, with the dogs and the cats, it's pretty obvious. You have a big giant dog and a big giant cat. But with the batsman and bowler, you may be looking at the jersey, the background, the people.
Yeah.
So they'll have a harder time knowing that it's the...
I mean, maybe something to signify that is a bowler and something to signify it's a batter, then it'll be able to distinguish quite easily.
Or you need a lot more training data.
No, but even if you have trained data, because each person is a different person, okay? It's not like he's not doing facial recognition.
Yeah,
each person is...
I think it's looking at what's common between all those batsmen, right?
Yeah, so basically when I search, so all these images are kind of like bowlers, they have this bowling arm up.
Okay.
And batsmen, they are in like stroke.
Oh, okay. Then it is okay.
So the ones it identified wrong is one batsman holding his bat up.
Yes.
Yeah.
This is the bowler.
Yeah.
That's a good way to look at what it's guessing and see where it's making mistakes.
Yeah.
And see what it's looking at.
Because that's one thing Jeremy says, okay, if you once you get that, you have to start looking at the images where it's getting incorrectly, because that's how you will know where it's missing things.
Actually, what I'm asking here is a TT. Yeah. So when you do this TT, transform each training set.
Not training set. This is the test set.
Oh, test set.
Test set, to make the prediction on the test set itself, it transforms a little bit, few different transforms it applies, and then it takes the average of that. Because it says sometimes, I mean, some transforms may work and some transforms may not work. We don't know that. Let's try a few transforms and then take an average. I mean, it's a similar thing as an ensemble model. Like when you used to Kaggle and all, what they would do is they would fit it for 4 or 5 different models. And what they will do is, and then take the average of the results. The average of the results, in fact, will be better than any one of the models. Because of the thing, what they say is, the models that got it wrong, sometimes may get, the other models may get it correct. So on average, you may get it, I mean, you won't be wrong quite a bit. Your chances of getting wrong are less and stuff. So there is a lot of, I mean, people win using ensemble models.
If for instance, the model in this case is focusing on, say, the ball or the bat, would it help to train specifically on those things and then apply it to the entire image? So for instance, just focus on bats and balls, and then apply that to the entire image of the player with the bats and the balls.
No, then you get into the bounding boxes and stuff. How does it know which is exactly is the bat?
No, so crop the images to where you just focus training on those things.
Yeah.
And then it'll find those in the bigger images.
But he doesn't know the bat may appear on he doesn't know where to crop it. How would he know if he had 100, 200 images? Where would he know how to?
Manually.
Then you are doing manual training, which is much harder stuff.
So that won't give a boost to the.
I mean, if you crop and train it, you could crop and train it with the bat and stuff, but when the image comes in, when the full image comes in, it won't know where to crop it.
On the full image, now it knows what a ball is and a bat is. So it knows these 2 classes. So on the full image, it knows when it sees those, okay, this is a batsman. Now it sees a ball. Okay, that's a ball.
It could, yeah, that could. I mean, but then you are saying as well, then the other way is just train it on bats and balls.
Basically.
Just take images of bats and balls, that will train it, and then try to use it on your bowler and batsman, because then it will try to, even if he's, all it's looking for is there a bat or a ball?
Yeah, bat, ball in a hand or a bat in a hand.
Yeah.
And then it would be better.
But I thought in your image, it only has the portion, it doesn't actually have the ball in his image. Yeah.
Also, they might have
Yeah.
a ball, but it's not like
prominently visible because it's hidden. Okay, you may not be able to see it, so that may not work either. So
good thing to try.
Yeah. You just have to try a few things and stuff and see. As you said, the transformation is something you can try. The TTA is something when you're trying to do predictions. TTA boosts the performance, and so that's, I mean, going back to this again, it's very hard to see, but I'm going to still open up the his Excel sheet one more time on the convolution, just so that we'll refresh ourselves before I go to courses, deal one, Excel, con example. Well, no, I have it downloaded, so I should just go here. Common example. Yeah, the same thing with the dog breeds. I mean, I didn't do anything. I got about 80% without doing much on it. Now I have to start doing things. I mean, that's 120 classes, so I have to start doing stuff. So here's where he's showing. I mean, here's what you start with an image. Again, this is only one scale image here, but he's doing this filter. I mean, we can change these filters to anything. I mean, ultimately the model finds the optimum filter. But if I change I mean, this is all it's doing is applying this filter across one set of area here, and then finding that's what is equal to. It's equal to applying this to this. So as it applies, and it is doing, and it's making, and also when you see this, he's also not allowing for negative numbers. That's something the convolution, because there can't be any negative pixels there. I mean, that's why he does a max on it, because there's no point having a negative thing. So that's something, but all it's doing is a sum product. I mean, not even a sum product. I mean, just a product, sum product. Yeah, the sum product. I mean, this times this plus this times that plus this times that and stuff. And you've gone from this image to kind of this image here. You've gone to a different thing that it is looking for. Suddenly you are getting, it's finding this edge here or something. That's what this convolution, the first layer, does. I mean, it's trying to find, because it doesn't know there is an edge, and it's trying to find some edges here and edges here. I mean, if we change this to something else, some other number, I mean, if I change this to -1, it'll be a different number, different image will come out of this convolution. And every time you see, I mean, it's finding these edges here. It's finding these edges. It's finding some edges here. It's probably not finding any edges at the top, because it is not. I mean, it's trying to find certain things on this image. But if I make it 0, it's a different thing. It won't change anything. If I make it a 1, then it finds certain things. Again, we don't know exactly what it, but this is the math. Math is that it tries to abstract away the image in some fashion. And each layer is building upon itself in itself, because once you have this, these are 2 filters here, which I've applied. And so I'm getting 2 images here, because these are 2 different filters, and 2 different filters will look at 2 different things. But when I go to the next layer, what happens is it's going to apply these 2 filters to both these images. and get this image from this. So the convolution now takes however many images if you take, if it found more images, it's going to, if there were three, I mean, if we had three filters, then there will be three images here, which will come out of the first convolution. And then the next layer of convolution was going to convolute with three filters here to produce one of these images here. It's going to convolute with three, because if you look at this, it goes and multiplies this with this, and it goes and multiplies with the next image here. And that's how the nonlinearity goes and develops. I mean, you're going from one, and it's looking at the whole set of all the images that have been convoluted, and then it's making a sum product and to come up with that. And these are different filters. Again, it's coming up with different filter weights. I mean, this is coming up with the different filter weights, and this is coming up with some different filters here, which will go and apply here. And as you go along, I mean, you're going to get something. And then the final, I mean, again, the next one, I don't know if it is a convolutional layer. He hasn't shown that. This is after a dropout. He's just dropping things out. Basically, he's dropping out on a 0.9 basis. If you do 0.5, it won't drop out. This is just an activation function. He's just dropping out some certain things. And then he's doing, after a dropout, he's doing a max pooling, saying, okay, I just want the max of, max pooling gets rid of, now suddenly you're gone from a 26 by 26, and the image size is much less because you won't have any numbers here. It'll be a smaller image when you do a max pooling. Because all the max pooling does is, it's taking two of those and creating one of those things. And then it's going to the next one. So it's not like when you do convolution, what will happen is this, if you do this max pooling, see, it goes from here, and then the next max pooling layer goes to the next set. But in a convolution network, it will slide along from here. If you go here, it'll be there. So that's the 3 by 3. If I go to the next 3 by 3, it'll slide one and then go across. It goes and slides across each of the thing, except that you go from a 28 to a 27 because you lose the edges. You lose the edge because you can't have a 3 by, you start with a 3 by 3. When you end up here, you can't go any further down. So you lose one layer there. 3 by 3. And there is formulas to kind of say, okay, what is the, if I do a convolution with a stride, I mean, when you call about a stride means, is it going to move by one row, or is it going to move by two rows and stuff? Or this way, is it going to move by one column this way, or two columns that way? That's the stride. And then this is just the filter size here, the filter size they specify. And if we go back to something I had here, and if you, this comes back to the same thing. If we go back to what I had here, this one where I showed something about what the model looks like. I don't know if it's going to load. Okay. It's not loading because it became a bigger file, I suppose. Huh. I'll have to go to my own thing here then. It's not even loading for some reason. don't know why Conda is not working for me. I have no idea. Oh, there it is. Okay. Wow. So, and let's talk about at least the fresh out things with the layer thing. And my fast AI. No idea why it's taking this long. Maybe with the Google Hangout and stuff, it's taking this long. Maybe. Yeah, this is what the model I said, the ResNet model. If you see here, they say the kernel size is 7 by 7. So that means that 64 filters, there'll be 64 filters, and the kernel size is 7 by 7. We looked at 3 by 3. When we looked at the Excel sheet, it's a 3 by 3. Here they are saying 64 filters, and then the kernel size is 7 by 7, and the stride is 2 by 2. That means it'll slide 2 rows this way and 2 columns this way when it goes this way. So it's not 1 by 1. It skips 1 row, basically. And then the padding is what they do is, again, you can add a padding around so that it doesn't lose that, it doesn't go from the 28 by 28 to 27 by 27. To preserve that, you can add a padding to that. What it'll do is it'll add zero padding across the top, so you still get back to your original size image when you do the convolution. And I mean, in fact, I mean, that's what it goes down to. It says it's convolution, and then the batch norms, we'll get into that later. And then the ReLU is your rectified linear unit, which just says here, that's not that we showed the dropout, all the rectified linear unit. Here he doesn't, because he's already done the rectified linear unit here. See, the way he has done is max of 0 and stuff. That's where he's done the ReLU automatically. The convolution won't do that. The max is what he's doing that, because the ReLU is just saying if it's -1, make it 0. If it's something else, then allow it to be whatever it is. So positive. See, he's already done it in his code there. But you actually do it. I mean, you convolute it, you do a batch norm, and then you do a ReLU, and then they do a max pool on that. And then it's just a repetition of that. But we'll get into the ResNet. There is some connections between one layer to the next layer. This doesn't show the connections here. All that shows is what the blocks are. We don't see the connections here. But when we build the ResNet, I mean, in lesson 7, I think of the last lesson, he builds the ResNet from scratch. That's where you will see what the connections are. Here you don't see, when I print the model, I don't see the connection between from layer 1 to the layer. It sends some information. That's what the residual network means. It's sending some residual information from one layer to the next layer. It's not just flowing across linearly. It's also sending some information from one layer to the next layer through a jump somewhere. Or again, I have to go through his course, the lesson 6 or lesson 7, I think, to see how exactly it does that. But it's just as a bunch of convolution. Again, 64. See, you're dealing with 3 because each image has 3, the RGB. That's why it starts with 3, and he applies 64 filters to it, to 3. Now, when he comes to the next thing, he has 64 images now, and he's applying 64 filters to the 64 images from the previous conv layer.
But not to each channel.
No, the channel is already collapsed. Once you do the 3, it's going to apply the filters to all the 3 channels, and it's going to sum product that and create one, create create the one of the filters. I mean, this is the filter weight. The kernel size is the filter weights. It's going to create not the filter. I mean, yeah, this is what they call the filter image. Yeah, it's going to create 164 by 64 images from that convolution. Like here, we have done one image here. Even if it had 3 channels, what this would do is if we apply this filter here, it will go and apply it to this channel plus the other channel plus the other channel to produce just one image, basically. And so when you apply 64, you're applying 64 weights like this to and each of the weights will apply to all the 3 by 3 to produce 64 images down there. Then when you come here, what he says is, then he applies another 64 filters to these 64 images. So what will it go is there'll be 64 weights. It'll go to each of those images and it'll create another 64 set of images now. With the kernel size of this. So did I do a summary or something? I don't know if I did a summary here. Probably not. I did a summary thing where it showed how many, I'm not sure if it is here, how many parameters are involved in this. Probably not here. This just only shows the model. It's doing something somewhere. Let me show how many parameters. Doing some tests and tests. This doesn't show the summary. I thought I had some. Oh yeah, that's called the summary. See, it's got the 224 by 224. And then the output shape will be 64. Because we are striding 2 by 2, we'll get the output shape was 112 by 112. It's going to be half the size. But you'll have 94,000 parameters to do this stuff. NB parameters, they're saying tensor is 94,000. Is that the parameters? It's the, what is it? I think is 112 by 100. What is the 94? I thought I had done a calculation of that because this only says it has a 128 parameters here, which is 94,000. I have to check the math. I mean, how does it come up with this math? Like ReLU has nothing. I mean, the batch norm has just batch norm. That's why it's a 128, and ReLU has no parameters. I mean, it just applies a ReLU. There's no parameters to it. But this 64 goes to 112 by 112 because you're doing another 2 by 2 on it. It'll go to 64, 56 by 56. No, sorry, he's doing a max pooling of it. Max pooling. So he's doing a max pooling. If you see here, it's doing a max pooling of it and a stride 2 by 2 on the max pooling and the kernel size of 3 by 3. I think because of the 2 by 2, it'll get down to something like what does it say? Model. It'll get down to 56 by 56 here. Just half of that. And then he's doing another convolution. He starts with 64 and then the 56 by 56. But in this convolution, he gets back 56 by 56 because of the stride is 1 by 1. So he doesn't lose, and he has padded it 1 by 1, so he won't lose one of the things. So the ResNet will come out with 112 by 100, where is it? 56 by 56, but with 64 filters there. But then they say is it requires 36,864 parameters to do that. So 9408, where is that? I do this. because I thought there was 64, there's 64 filters out there, and then they're doing it by, and then there are what, 7 by 7? I mean, I just want to check if that's what gives me the answer. 7 into 7 is 49, 64 times, I should come close. Well, I don't, because what is the part of, there was 7 by 7 filters, and then there are 64 of this, and getting 3, and this is actually 94,008, because of the weights, and then there's the bias.
It's 64 times 3 times 49.
Oh, yeah. Oh, is it? Okay. Oh, really? Yeah, I get that. 9408. So I was thinking of the 3. So it is requiring, because I thought the 3 is already there. I thought it was going to convolute the 3, but then it requires, is it applying that many parameters? So it is applying a different, I mean, it's creating 64, ultimately a 64 images out of that, 112 by 112 of 64 images. But then it's doing is, it's taking 64 filters, and that filter size is 7 by 7, so that's 49.
And it sounds like keeping all 3.
It's keeping all 3. So it's applying different filters for each of the channels.
Yeah.
Each of the channels.
Otherwise, you will lose that color information right away, right?
Okay. But then how is it? But it's only producing 64 images though, out of that. Even though it is having 64 by 3, even though it is having, it's having for each of the channels, it has a different, okay. That's what it's coming out to, is for each of the channels, it's having a different filter for each of the channels, but it's summing the product out of that. Okay, it's not applying the same filter to each of the channels, the 3 channels. It's applying 3 different filters to the 3 different images, but then it'll create one picture out of that. So it'll sum all the things to prevent one thing. So so that's how it is coming out. For one filter, each image is going to have 3 sets of weights, 3 sets of filter weights to do that. So say you get the 7 by 7 is your filter size, times 3 is your 49 times 3 is your thing for each filter. Now we have 64 filters like that, and so we times 64 on that. So what would happen is, if we had the 3 channels, we would have another 3 here and another 3 here, and those 3 will operate on that to produce this image here. That's what is happening. Which, like here, that's what he's doing. Here he has 2 filters, which is operating on these 2 that was created from here, and that's how he's getting that. So as the number of things go on, so if we look at that, let's look at the math here. Now it is even higher. See, that has become, it was 9408 now, that has become 36,864, because what is happening is, it started with 64, 56, 56, 64, 56, 56. So what will happen is, this is getting interesting. So this basic block has kernel size of 3 by 3. So if we go here, so the 3 by 3 is going to create 9 first. So that's there. And then, but it sees, it's going to take 64 weights, like 64 of these 9 weights. So there is going to be 64 by 9. You're going to get there, 576. And then on top of that, that is only for one image. To create that one image, you're going to require this many things, but then you are doing 64 filters. So it should be 64 times this, 36. Let me check. I think I missed something. Yeah, 36,864. 36,864. So that's what is the convolution is getting at. I don't know if you guys got it or you see what is happening in the second layer. She said we can write on this this thing, the second layer. So the first thing is we've got 3 images, 3 channels in the first thing. So what it's doing is we've got a 7 by 7. We got a 7 by 7 here. So it's going to create 3 7 by 7, as you say, to distinguish between the colors and stuff. It's going to create that, and then convolute. This filter will apply to this. This filter will apply to this. This filter will, on all of these will be some product into making one image out here. That's how for one image here, you're going to have 3 of these 7 by 7 filters to create one, and then what happens is this is just one filter, because it's only creating one filter image here, one filter, but it requires 7 by 7 times 3 parameters, 49 by 3 parameters. It's going to require 49 by 3 parameters, and in the same way, this is just one. This one filter has 3 different weights, and then it's going to do another set of like this, another set of like this. So you're going to have 64 of these things, creating 64 convolutions. The first layer. That's how this becomes 49 into 3 into 64. Is it 49 into 3 into 64? Okay. Yeah, that's what it was, 49 into 3 into 64. That's how you got the 9,408. The next step, once you've got all the 64, when you go to the next one, now what it's going to do is to create just one image of this in this layer, layer 2. This filter, this thing is going to have weights here, weights applying here, down to 64 weights. This one image is going to have this. The next image is going to have its own set of 64 filters to apply convolution to on this. And so that way you have 3 by 3 here. So you will have 64 times 3 by 3, but you also have 64 of these because I want to create, so it is 64 times of this. So you get to this 36, 34, something like that. So the convolution is actually happening. It's not just this one image from this layer. It's not just convoluting with one image here. It's convoluting with all the images here with a different set of filter weights here. And then the next image has its own filter weights, which is convoluting with this. So as it goes along, this is how it's able to distinguish, slowly learn. I mean, it changes all these parameters here and slowly learns, because it's all random. You're starting with random things. So one set of filter weights will start learning some feature, another set of filter weights will start learning some other feature in that image. And as we go along, you'll see it keeps increasing, and the number of parameters will keep increasing more. So you just want to at least try understand what the convolution is doing. It's not just applying one set of filter weight to one. I mean, when you do a convolution from 64 images to another 64 images, you have to create for each one of them, you have to have 64 filter weights to do that. And then the same logic, if you go on this next one, what is it? What is it? That was 36,864. It'll come down to the same 36,864 because all we are doing in Con2B is it's not going to increase anymore, because all it's doing in the Con2, this layer 2, I think Con2D here is, all it's doing is the same. It's doing, no, 64. It's actually going into, no, I was looking at 64 by 64 here because this layer itself has two cons here, two con nets here. This layer itself has two con, which is just the same thing, 64 by 64, 64 by 64. They're just repeating it again two times there. But the second layer, it's going to go from 64 to 128. It's going to blow up more. It's going to create from 64 images. It's going to create 128 images. That's going to increase the number of parameters quite a bit. Because what will happen is, and it's going to do a stride of 3 by 3. So to create this 128 images, it's going to go 64. So we start with 9, which is the 3 by 3. And then it's going to do is each of these images here has to do 64 weights of that. So 64 by 9. So that's the same thing as we did before, 64 by 9. And then now there are 128 images it's going to create. So it's 128 by 576. So we should get to about 73,728 parameters now. That will be needed. And we should get something like that. No, I think I'm not correct. I'm not getting that. Maybe come too far.
That stride, 2 by 2.
Oh, the stride. I didn't see the stride. Okay. Yeah, if it's a 2 by 2 stride, divided by 2. If it's a 2 by 2 stride, it's going to be divided by 2 because it's missing things. No, that shouldn't. That should only change the size.
Not the weights.
Not the weights. It shouldn't change the weights. But let me look at, is it called con1? I got to make sure I'm looking at that. Layer 2, 64 by 128. Let me look at, make sure. Where does it go to 128? This is all 56. This is all 56. Because I'm still looking at something. I've not gone into. Okay, this must be a different model summary then. I'm not getting, oh, here is where I'm getting into. Okay, I know what I'm looking at, two different models, maybe. What kind of, this was a ResNet 34, and then I was using a ResNet 18 here, I think. That's why I'm not seeing the same thing, because I was using a ResNet 18. Okay, that's why I was not. Maybe initially they were the same. So after that it is, but that's a logic. It'll come to that. Okay. I'm just comparing two different ResNet. It just happened to be that the first few things were similar, and after that, it's not even going. The input shape is not going to 128 and stuff. But when it does go to 128, I'm seeing that it goes to that 73,728 here. It's not just coming there. So, I mean, that's why these parameters, I mean, in the deep learning, there are so many more parameters. When you get down to this 128, when 128 goes to 128, you're going to get up to like more than, it's like 147,000 parameters on that. And so all this stuff adds up. I mean, they keep adding up, and 147,000, all of those things have to be changed in some fashion or the other, and it goes through and changes in some fashion or the other, all these parameters to get to your convergence.
What's that negative one?
The negative one, don't worry about. This is how that model summary is. It's just saying there is nothing. This negative one is a batch. What will happen is when you put something into, when you put data into this, the first dimension is the batch size. If you have 64, here I'm not putting a batch. I'm just putting only 224. I'm not putting a batch. I'm not putting 128 images into it. But that's just, all it does is that's just, I'm putting it as a batch, and it just treats, it does 128 at a time. That's just the batch. So don't worry about the -1 there. But that's just an insight into the convolution thing, convolutional network and stuff. So if you want, what do you want to go on things? I mean, I know you guys have worked on it, and I mean, you had some errors and stuff. Other than that, I mean, I don't know how much to cover on lesson 1. I mean, without getting into too much into depth into bash. I mean, if you have to get into batch norm and all, first you have to know the fundamentals of batch norm, what it does and all that stuff. And he doesn't do it until later. He doesn't want people to, he wants people to get an idea of what it is and all that. I mean, get an idea of how things work and stuff before doing things. So I showed you the planet data last time. I mean, that's something we can look at that, but it's no different than this, except that we use a different loss function. Loss function, which is geared towards, which is the multi-label thing. Okay, this doesn't work. Okay, let me go to this. No, this one. It's just the same thing you do. This is just a collab thing I was doing. I mean, if you follow along, it's just that they have a training set of images, and they have a CSV file that tells you what the names of the images are. So if you look at that, I mean, the files are like this. If you look at this thing if you look at the planet thing here, I mean, it's all the same. If you look at that, let me see the planet data set. I thought I had it. Nope, I have it here. Planet. Nope, that was somebody's data. No, the train.gpg. I mean, this is just satellite images after satellite images out there. And what they've done is each of those satellite images, they've gone and if you look at the train in CSV2, they've said, hey, that's train 0. The labels are haze and primary, agriculture, clear, primary, water. So it's not just one class. They've applied multiple classes to that. So the object of that competition was, okay, can you predict if you see that? How close can you predict all the classes that it belongs to? So this would be agriculture. It is clear image. It's a cultivation. It's a primary. I mean, primary is there most of the times. It's a primary. I have no idea they don't tell you what primary means. Okay, it's like we don't. I mean, that's not the part. Yeah, we don't need to know about this unless you are in that. It's just a label. Okay, it's just a label. Ultimately, it's a label. And all I've done is, hey, I did what I did was, I mean, just you can apply some different transformations. There's some brightness transformations that's there so that you can bring it more brightness or things like that. I've seen in Kaggle some of the competitors are playing around with brightness on that on things. So they've just said, hey, that may help. And then you can do, again, you have to crop it to 224 in some fashion or the other because that's what the ImageNet size is.
The only difference, you can do the vertical on this.
Yeah, you can do random rotation. I'm doing some random rotation I was doing, and you can do vertical flip too on this. So a few things. You can try a few things on that you can't usually try on like animals or human images. And the only difference, as I said, if you do this, I mean, this is the haze and the primary, this is the agriculture. I just plotted that. It's just a different, I had to create a multi-label data folder to do this, to handle this, because this is not in a fashion where you have folders with the class name of the folders. All you have is you have the set of images and you have a CSV file that tells you what image goes with what label. So I had to create a different loading function for that.
So you have to put the file into multiple folders when they have
no, you don't
labels,
have to. No, that's not how they do that. Because it's a lot of work. Why would you do that? I mean, you would as well ask Python to do it for you rather than try to put that into multiple
No, I mean
images.
automatically. Does it do it?
No, you don't, because you can't, because this is again not multiple, because this is not one class. So you can't even do your thing where you, because in the multiple classes, so you can't even put that. So it becomes harder.
So it's not really a data folder.
No, it's not a data folder. Yeah, so it's just a bunch of images with labels. So yeah, it's not a data folder. I actually went and changed it. This was an older thing. I actually went and changed it. So I left it like this for backwardness.
That's what they call it in FastAI?
No, they don't call
Or is
this.
that for Torch?
No, this is not Torch specific either. I had to write this up. Okay, if you see this, I'm actually importing this thing where I wrote something from somebody else on the Kaggle. I had like copied how he did that and stuff. So you can, I can show you the code there, but it's just, I just took it from somebody. Okay, and all it does is it'll load it. And the way is here, if you see the classes in multiple classes, not the multiple labels, in the multiple classes, the output is only one class. It'll be only one class. It's either going to be dog, a cat, or something like that. What we usually do with that is we just say the class is going to be 1, 2, 3, 4, 5, or something like that, and we pick the argmax of what it which index it predicted and stuff. Here, since you're predicting multiple classes, you actually have to, the output is not just one. It's a multiple zeros with labels for what class it is, what class it belongs to. So this would belong to this class and this class. See, here is all the classes. See, all the classes are here. It's about 17 classes. Agriculture, artisanal, bare ground, blooming, blowdown, all that stuff. Okay, and if it means one here, that is what is it? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here, if I go here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it must be Hayes, and Hayes with primary on it. So that's why it's two classes there. So since it is a different output, here is where you have to do, it's exactly the same thing as we did for dogs and cats. You can do ResNet 18 or ResNet 34. And all we are doing is changing the last fully connected layer. Instead of out features, we are saying 17 features out, basically. 17 features are going to come out. So it's going to predict 17 stuff. But the only thing that is different is you use this, instead of the stuff that we used to use, softmax and stuff, the NLL loss, the log likelihood loss, and you have to use something called a multi-label soft margin loss. That's something PyTorch has defined, and you can go into it to see what exactly it is. But they have defined, if you have multi-labels, you can use that. That's one of the soft margin loss. You go there. He's just giving you an example of what it is. But yeah, multi-label soft margin loss. Soft margin loss. Again, this is the equation it does. Okay, the soft margin loss does this, creates a criterion that optimizes a two-class. No, multi-label. I gotta go multi-label. That's not. Multi-label soft. Yeah. So it's it optimizes a multi-label one versus all loss based on max entropy between X and target Y of size N and C. So size N is N is always the batch here. The C is the number of classes. So you have to have 17 classes there. So it's going to go and apply this formula again. You can look at that. This is what they say in theory as to how do you optimize the loss function for a multi-label class, because the output is not just one class, it's multiple classes coming out of it. And you can think of other use cases. This is just, he uses the Planet data set because it's a useful thing. If you create something with 2 classes, images with multiple classes with it, and you can ask it to predict what those 2 classes are. It's like somebody, maybe a cricketer having a bat and something else or something. You can put other labels to it rather than just one class. But you have to, what you have to do is you have to create those images and you have to assign it here, as you say here, assign it what classes they belong to. So it's helpful in certain cases. Hey, I want to predict, I just don't want just one class out there. And you will see where this becomes more useful is where they do things with the bounding bar. Because in lesson 8, when he goes to deep learning 2, course 2, what he does is he not only predicts one, I mean, it's a different thing there. I mean, the top 5K, whatever they used to predict, as the other thing is what, if you look at ImageNet, they not only used to be in the competition, it's not about the predicting that just the one class, predicting the top 5 classes. But that doesn't use this methodology. All they do is, what's the first highest probability, and then the next highest probability, and the next highest probability, and they say, what are the top 5 probabilities in that thing?
So I forget how it was before. So are they using a threshold?
Yes, threshold to predict the classes. Again, the threshold what you have to do is you have to experiment with the threshold. Which one threshold predicts the best? So there is a little bit more towards it than just putting the losses here, because it could change based on, where am I? The GitHub site. Because I'm saying calculate loss. Yeah, the multi-label soft margin loss is this thing. But how do you actually, yeah, this is the F beta score. I think I had an F beta score. I thought I had changed it, but I haven't. Yeah, see here, I have defined something called F beta score, which would be, did I do it here or did I, let me, oh, F beta score is something that comes with the sklearn, F beta score. So that's one thing. How do you calculate the accuracy of your prediction? So that's something, yeah, the loss is fine. So it keeps optimizing it for the loss, but how do I know how accurate I am? So that's something, if you go here, again, sklearn has the F beta score, which they say is the weighted harmonic mean of precision recall. Okay. That's not, yeah, it's something.
It's much more useful.
Yeah. It's much
the
recall and the precision together in there. So it's much more, yeah, because how do you know what is accuracy? Because you can't in a multiple label, how do you know what is accuracy? It's difficult to know. I mean, you have to then, because it's not just one class you're measuring against, because usually in the multiple classes, you're saying, hey, how close was it to my class or not? Whether it gets a 0 if it doesn't predict the right class, it's right or wrong. Here, you can't say it's right or wrong. Which is why they use this F beta score, weighted positive score of the positive class and binary weighted average of the F beta score of each class for the multi-class task of each class.
But each image would have only certain classes, right? They would have to get those, right? So like
No, each image, it says some 3 classes.
Right.
And the right one is say 4 classes. So how do you know what is accuracy there? There is no, what if, so it got 3 classes right, but that is not 100% accurate. It didn't recall everything. So you have to know the precision recall. Yeah, so that's why they go through a precision recall. It's something, it's a weighted harmonic mean of the precision and recall reaching its optimal value of 1 and its worst value of 2. So it's some mean of the precision and recall, because sometimes what if it didn't recall all the, it was precise, it did get 3 of the things right, but it didn't recall all the 4 though. It's F beta score is different from the F score. There's also an F score, I think.
I mean, it looks like F score is the
average of precision and recall.
Yeah, it's the average of the precision recall. I think this is some harmonic mean or something like that. It's slightly different. F score. I do F score, F1 score. Yeah, F1 score is a measure of the test accuracy. Is a measure of, it considers both precision and the recall to compute things, okay. But it must be like the average of, no, the traditional measure is the harmonic mean of precision and recall. Okay. It's the same thing then. F beta. See, if F beta, positive real beta, the general formula of positive real beta is this, type 1 and type 2. So it is the same thing. Is also known as the, okay, some other things. So it's the same F score, F score only. The name F measure is believed to be named after, it's a harmonic mean of this thing. All it does is say it's 2 divided by 1 by recall plus 1 by precision. So it is some thing of precision times recall divided by precision plus recall. So in these multi-label classes, you have to use a different way to measure your accuracy.
So once if you change beta, it gives weight towards precision or recall, right?
No, there is no beta. Oh, this beta, the general formula for positive real beta is, yes, it may give different weight to, yeah, to precision versus recall. You can play around with it, but that comes, yeah. This general formula is for beta is 1. No, but yeah, beta is 1 because it becomes 2 and stuff. Yeah.
If it was F2,
yeah.
More towards in that case.
Yeah, F1, F2 is towards weighting more towards a precision. Is it?
So F1 beta means recall is beta, right? Because it's in the denominator.
Yeah, it's in the denominator. So it will increase your precision more, and then it will decrease the, that means it increases the, but then if the precision is high,
you get
lower scores. But if the precision is low, yeah, it'll get, yeah. So that's where you play around with what is your cost for precision versus recall. I mean, if I get the false positives or the false negatives, what is my cost? Am I, because that's where you will get into how do I choose a beta. So because then I can tune in for a certain beta based on the cost. Because the beta, you can assign a cost for that. You can ultimately find the beta based on a cost for the false positives and the false negatives. If your false negatives are more important than the false positives, then you give more weightage to that. And that's how you give more weightage to precision or recall. So it's some fashion we are giving weightage to precision or recall, because see the true positives and the true it comes down to this. Which has more weightage, which has more cost to it. Then you will adjust your beta towards that. Because if your false positive is more important, I think you will I have to do the math and see how it works there.
False positive looks like it's going to be heavier weighted.
Yeah, if the beta is higher, I think, yeah, okay. So the false positive is going to be heavily weighted. So that means we care about, yeah, which makes sense. We care about false positives more than the false negatives, and so here, all you do is, I mean, you come up with some F beta score you have to have a threshold for it to choose from. And I think this is this beta 2 or what did I use there? Because I just copied it from somebody, some Kaggle competitor who used that. So I gotta go and see. Yeah, this is the beta. The Y prediction and stuff. It's the beta. Targets, the outputs, and then the beta, I've put it as 2. Because because they actually asked us to do it, because the Kaggle competition, if I go to the Kaggle competition, they actually said this is how we are going to judge the thing. Kaggle, if you go here, the planet understanding the competition, evaluation. In the evaluation, they said beta equal to 2. That's why you use beta equal to 2.
So didn't beta recall is more important. Yes.
Yeah.
So that's how they evaluate. Normally the F scores are like what you use for evaluation.
Note that F2 score weights recall higher than precision here. Yeah, recall is better than precision. That's why they do a 2 here, which means they're saying recall is higher than precision. So they want all the labels, I suppose, of all the possible labels, then leaving out the labels. I think that's how the recall, I mean, have you actually gotten all the things that should be called in? Yeah.
They'll use labeling more than mislabeling.
Yeah.
More false positive.
Right?
False positive. Isn't it based on the false positive if it's recall?
It's the true positives to all actual positives.
Yeah, recall. It's weighing recall higher than precision. So true positives by true positives plus false negatives. So the true, okay, false negatives. It wants less false negatives then. It wants less false negatives. You have to think through in multi-label how that works, okay? It's easy to see it in normal things, whether it brings up or not. Multi-label, you have to think through what it means. So it's the same thing again. As you say, you do the same thing again. You just change the one thing is the soft margin loss. You use that to optimize your loss function. And the metric, say accuracy metric is different. It's an F beta score. And you run the same thing. I mean, you do all the same steps on this. And I mean, I didn't push too much forward. I mean, I got 82 and stuff. I just haven't pushed too much forward on that to get a higher score, higher accuracy score on that 82. Because 82 is not going to win. It's about 91 or something. You got to 93. Okay. So, but he gets about like 80. He gets 91 or 92 in his thing. You just have to, because then you have to train some few layers at the back and stuff, and you have to do a few more things than just having one fully connected layer. And remember, as I was told in Fast AI, he just not only, I mean, we've used for simplification, we've done this, but if you go here, which I did put in my GitHub thing, he doesn't use just I put it on the wiki there. Organization. I had a note there. Comments on one comment I made is they have a few other layers. They just don't replace the fully connect. All what we've done is we've just taken the ResNet and just set fully connected layer equal to the number of classes there, however much we want. But what he does is he adds all these stuff to it. I mean, the log softmax, we have that, but he's not just replacing this linear features equal out features. He adds a bunch of other things above that. And that helps some of the accuracy. All he's doing is he's adding some batch norms and flatten and linear layers and ReLUs and stuff. So he's adding a few layers after the end of the ResNet and between the fully connected layers. So going back to this, as I said, this planet, I mean, you can try this. I've got the collab notebook out there on this. I mean, this should be the collab notebook. Yeah, this is the collab notebook. So you should be able to run it and get a feel for it. You can change things and stuff, and you can do. It's just a multi-label. He's just saying, hey, we've done a lot of multi-classes. It's a multi-label problem. And on this, again, you have to do some all I've done is I've used, as I said, I've used a threshold here. I didn't know this. He just said, Jeremy said, hey, 0.2 is a good threshold. I've experimented with it. So I just used 0.2. You could use 0.16 or 0.18 and see if the accuracy changes. I mean, after you even train the model, you can try to see if the accuracy changes. You can run a batch and see if the accuracy changes. And he uses TTA, the test time augmentation, all that stuff, all the good tricks he uses to get his high number on that. So the next thing after that he talks about, so we've talked quite a bit on this. The next thing I just want to comment on is this. If you guys want to take a look at the lesson 3, which is the columnar data set. It's a very, very long lesson when you go even here. If you go here on this, why it is long is because you have to do, before you get to deep learning in a columnar data set, you have to do a bunch of feature engineering before you even get there.
This is the last one?
Yeah, this is the last one. That's his lesson 3. This is the structured data. That's why it's a long thing, but go through that, you will see what are all the stuff he's doing. But because any columnar data, any data set, you have to do this because there is no other way.
Categories. How does it take categories? Go with that.
Huh?
Like categories.
Yeah.
Like it's not like continuous variables. You have to include the categories like Monday, Tuesday, Wednesday.
Oh yeah.
Yeah, that's why that's part of this.
No, but yeah, no model is going to be able to know what Monday is. Okay, so Monday, Tuesday is easy. Okay, that's not a problem because Monday, Tuesday, it just keeps repeating itself. Monday, you can always say all you do is you replace Monday with 1 and Tuesday with 2, 3, and 4. What is more important is he says, well, I have to now do the state. There are public holidays. He has to put where the public, because all these sales and all that stuff matters in terms of when the public holiday is. And then he has to go and say, how many days before the public holiday is this date? Is it 1 day before the public holiday, 2 days before? So he picks up
Depends on how you're storing it. It depends on how you're storing it.
Yeah.
If you're just doing a recycling week, that gets to be a little bit hard.
No. That's why you have to store it in a different variable. You can't just store it in that. Week is just 1, 2, 3, 4 is just a day. Then he has a separate column. If you go through this, he has a separate column because all he gets is, hey, this is the training set provided by the competition. And then they provided a list of stores.
You want to do the categorical embeddings too?
Oh, yeah. You'll have to do the categorical embeddings and all that stuff. But before you get there, the deep learning is only 10% of the work. The 90% of the work is preparing the feature engineering here. And it's not even, when I looked at, when you get to the deep learning, you can get I can easily get what is the Rossman thing? If I look at Rossman, what was the Kaggle Rossman, what was the leaderboard on that? I just want to see the leaderboard, how much they got. Maybe it's not Rossman, is it? Rossman store source competition. So the leaderboard, I don't get this, how somebody is cheater. How do you even get this? Cheater. I don't know how they cheat that, but they're somehow okay. With the deep learning, I can easily get to number 10, number 9. Like I can get to 0.1 easily, 0.1 loss thing easily. Okay,
it's your variation from the true.
Huh?
That's your variation
from the true. Yeah, from the true forecast. That's the variation from the true forecast. Because all they do is, okay, I've given you a bunch of historical data.
Yeah.
And you have to forecast these 2 months of store sales or something like that.
So it's the same as stats.
Yeah. Yeah. And he's saying, okay, and then you try to predict that and how different it is. I mean, the test set is historical data, excluding sales. Yeah, and it's again based on they've not given you the sales. You have to predict the sales for each of the stores in the test data for those months, and they've given you all the dates and all that stuff, and they've given you the information about the stores. But what you have to do is when he does this, let me go back. Where is it?
How do you even cheat on that? You have
I don't
your
know.
model capture.
I don't know how you cheat on that.
You can look at the validation data.
The competition is different than this. Is that the same?
Oh,
This one is a different score.
Oh, this is 25 teams. So this must be something different in class.
This is the official one.
Oh, this is so in Kaggle. I didn't realize that you can also actually have somebody creating this thing.
The one with the red.
This one?
Yeah.
Okay, why is that? So all these, they have some school classes, they can create their own competition? Okay, I don't know. Yeah, this 0.01010 something. And Fast AI, he does that. I mean, he says he's there somewhere here. He said, I don't know where Jeremy is now, but I don't know if he submits under the name Jeremy or what he does. But you can easily get with deep learning somewhere here, easily. I mean, with his code.
Students too.
Yeah, his students too from Fast AI. So it's very easy to get 0.10 or 0.11 or 0.1085. The thing is, but before you get there, you have to do a whole lot of things. What he does is he actually takes data from other thing called Google Trend. Google Trend is a certain Google keywords over time found by users to correlate well with given data. So he's getting some outside data that's even outside of the competition. And then the weather data, because he says, hey, weather is going to change, weather is going to be some influencer of the sales. So he's getting weather data. Because remember, he knows the dates in which he's going to predict that, and he already knows the weather. That's already there. Because he's not sitting today and saying, I got to predict the future 1 month sale where I don't know the weather. The test set already is a historical date on the test set. And so he knows what the weather is. So he's able to use the weather to do that. And so the stores, the store states, the state names, these are the two things he brings in from outside. These are the stuff that's being given. These are the two things he gives from outside.
It's using Pandas data frame.
Yeah, Pandas data frame. The whole way. He's just using Pandas data frame.
You know that Google Trend is that in a CDN or is that just historical data they've compiled? Oh, they have an API.
So Google Trends.
There we go. That's useful.
You just give it a date and it gives you
the stuff.
Okay. So you can do that live. That's important.
Yeah. So it's Google Trends API offers a layer for Google Trends data that can be used to retrieve keyword popularity date by location and date. Several methods. Okay. So somebody, what he does, he says is, hey, I've taken somebody in the Google competition had done that, Kaggle competition had done this Google Trends for this data set. Yeah, he'd opened it to everybody and then he used it. So, because the Google Trends, what does he use? The table names, because I had that thing here, because that's one thing you may want to check it out. Google Rossman. Whether Google Trend.csv, what does it have? I don't know what this means. Trend is 96. Does it mean people who searched for Rossman maybe? I don't know. Oh, for that store, because see, this is Rossman DE. It's defined by the different stores or something. BY, TH, Northwest, RP. So this must be some code thing, if you go into his thing, he may be joining it based on something. See, he shows what the trend is, DESN. So this file name must be, he's showing all the things here, but then this has something he joins it with. He must be joining this Google trend with something. I mean, he does all these joins later on. Or does he already done it? Left on.
Join DF. Yeah.
Yeah, join DF, but which one is he joining?
That's later.
That's just later, yeah. That's just defining what the join is. He's just defining
Well, they're joining
Google
the weather.
trend. Yeah, Google trend state, he's just saying state equal to NI is state equal to HB NI. Google trend dot locate the thing, Google trend dot state. Okay, he's already split that. Okay, the underscore he split it, and the dash he split it. So the underscore is got to be the underscore is, he's already split that thing. The underscore, so he gets the DE and the BW there. Underscore and expand true, Google trend, if it's NI, he's saying we are also going to replace all instances of the state name NI to match the usage in the rest of the data, HB NI. So it's a good opportunity to highlight the pandas. We can use the, okay. So the Google trend.state equal to NI by selecting the state. State name, these are German store. So it doesn't reflect any of the states here. So NI must be a German store somewhere, German state. So here it is, yeah. Okay, if we can pronounce it. So that's what he's doing there. And I think this Google trend says is how many people have searched for that state or something like that, must be. And Rossmann, keyword Rossmann in that state. I'm thinking we just have to look through and see what it is. But it's some useful information for him. He just says, hey, that's found useful. And then he adds the weather. And then he does all the, I mean, initially he does all the joins and stuff. He keeps joining and joining and joining. And then he starts doing some NAs and not available and all that stuff with other stuff. If it is NA, he just says 1900, which is some no date and stuff. Promos to sincere and all that stuff he does. Competition open sincere and all that. Those are all given. Competition day, competitions open month and all that stuff. But he is, and he's limiting, he's doing something. I mean, you have to go through it to see what he's doing in all these feature engineering. Because he says that's ultimately how you get these models to work. You just keep doing feature engineering, and the duration is, and there are time series data is running averages, time until next event, time since last event. This is where he is adding stuff like state holiday and school holiday, time since a school holiday, and then time after a school holiday, so that he can see if there is any correlation. Maybe there is 2 days before a school holiday or 2 days before a state holiday, there may be a bigger rush and stuff like that. So,
yeah, he mentions that one of the teams, they eliminated the closing stuff.
Yeah, that he says he shouldn't have done that.
They lost
the first place or something they could have lost because of that.
It spikes right before closing.
Yeah.
And right after you open, it spikes.
Sure,
so
yeah.
You want the model to be able to understand the closings. So you want to
yeah.
that from
the thing. Because the store is closed on that day, but you don't want to remove that closed, because they had said if the store doesn't have any zero sales or something, they remove that data. But it's actually, he says, Jeremy, that's actually useful data, because you'd see a spike right after it closed, it opens, you'll see a spike, and that's useful to know. So.
Also, I would pay special attention to the categorical embeddings, because that can tell you a lot. Like, he plots the locations of the stores based on the categorical embeddings. It basically gave you a map of Germany. I don't know if you remember.
Oh, yeah, I remember that. Yes.
Very useful.
when you do the categorical, when you actually get the embeddings, because the model will learn the embeddings, and then after that you can plot that embeddings and say and see.
It gives a lot deeper understanding for the model besides just Monday, Tuesday.
And you can see these 40 columns he's made. I mean, some of them are already there, the state holiday and stuff, but he's made all this stuff, the distance to the competition. How much is the open since month, the competition open since, or the promotion since week, since year. And he's also said he's done these holidays don't show up, because there is not just 40 columns. Ultimately, he comes up with some 100 columns or something like that in there. This is just putting some 40 columns is there. So he does that. And then he does this categorical variables. Hey, these are my categorical variables and these are my continuous variables. So that he can only focus, he can put embeddings on the categorical variables and then not put any embeddings on the linear, on the variables that are continuous variables. So he goes across that. I mean, you have to sit down and look through each of that thing. Okay, once he has done that, now is he coming down to saying, okay, now he's just splitting the data. One thing he does here, and that's also for the images, where he says, okay, first train it with the smaller size image, the model, and then try to train it with the bigger size image. He takes the same approach here. What he does is he takes a smaller portion of the train data, and then trains the model, and then he expands it to the whole data. Because he says I can get faster training by that way. Because I'm starting from scratch. I want to do fast training. So I take 1/4 of the data initially and then train the model. Then I'll get somewhere close. Then if I put the whole data, now it can converge faster. So again, this is stuff until here, it's not even deep learning. Until this stuff, he's just splitting data and stuff. So here's where the deep learning starts, which is like down 3/4 of the notebook. And he uses, this is a metric that has been defined by the Kaggle competition. Okay, again, as we saw the F-beta score metric, they define this metric. This is how they're going to measure your accuracy. It's an exponential root mean square error, basically. Exponential root mean square error, because the sales are like in the 5,000s and stuff, and then they do certain things and like 50,000 and stuff, and he takes a log of that, and then he comes and does an exponential measure of this stuff. This is the percentage. I mean, ultimately it comes to the percentage variation. This is how they defined it. Okay, this is a metric that they've defined it. And this is where then he loads in the data. And if you see, these are the categories. He says, hey, the stores, there is 1,116 categories of stores. There is 8 days. Okay, 8 days of the week. There's only 7 days of the week, but there is a 0. If there is nothing not available, he makes it a 0. That's why you get the day of the week as 8 days of the week. Oh, because he's using certain things. He's saying if there is no data, make it 0. So that's why it becomes,
category. Those are each day of the
week is a category. So he's saying 1, 2, 3, 4, 5, 6. So that's a category. Yeah, cardinality. I mean, these are the state holidays. There are 3 state holidays, and then there is how many competition months open. There's 26 different competition months open and stuff like that. So these are just, cardinality of that store type. There are 5 different store types and all that stuff. So he's going to put the 4 different state holidays before, after, and stuff like that. So he's using, because he's only tracking 4 backwards and 4 forwards. That's why he's got only 4 of them. He says, I'm going to track 4 backwards and 4 forwards. I'm not going to track that much. He's just going to track 4 days before, 4 days after. But the school holiday, he's saying, I'm going to track 9 days forward, 9 days backwards. So that's how it comes out. Again, okay, why did he choose that? You can question that, but that's what he did. I mean, again, this is all. And a lot of this is also public. Kaggle people have done this and stuff. And then they said they found, I mean, people report on, I mean, they play around with things and people report on it. And ultimately you end up with this.
It's probably easier if you live in Germany, at least in Europe, because it's It's probably people who live in Germany or at least in Europe probably have advantage because they have domain knowledge. Stores, I know stores close in Germany early, and they close on weekends, not like in here, and they close on holidays probably. So you kind of, if you live in Germany, you're probably better off knowing.
For each of these companies, if you have domain knowledge.
Domain knowledge, you'll be better off. In these things, domain knowledge pays a thing. So he's just saying now that I know all the cardinality, he's saying how much embeddings I'm going to bear thing. I mean, there is a rule of thumb he uses how much embedding he's going to use for that. So you can go through, ultimately it comes down to, this is the model. I mean, I'll show you what the model he uses. He doesn't show you this, but in my thing, I showed what the model was. Where is it? I thought I opened, okay. And if you open my stuff, you will see I did all that. I just said, hey, until start from line 75 of fast ALS, and because that's all it's done. So if you, this is all that stuff that is getting done in the behind. Let me show you what the model finally, this is what we saw, this 116 and stuff. I thought I had the model at the bottom here. So this is all the model does. This is his deep learning model. There is these embeddings. Basically, there's 50, we saw all these embeddings. There's going to be that many categorical embeddings out there. I think there was, what, 20, like, okay, 22 categorical variables. So he's got 22 categorical variables, and they all, I mean, the embedding, what it does is, and then he has some dropouts and stuff. And then there is a linear things that join with the embedding here, with the embeddings. I think what, 22? Oh, you don't know? Okay, that's something. Explain it. That's stuff. Okay, yeah. Check out the embeddings. So ultimately, what happens is he starts with all these embeddings, and then the linear things, he joins all these embeddings as a concatenating thing. He's putting these embeddings together, everything, and then he runs it across a linear layer that will have 1,000 outputs, basically, essentially at the end. He runs it across 1,000 layers, and then he has a dropout, and he runs the 1,000 to a 500, a dropout, and then the 500 to 1. Because essentially, ultimately, he wants to predict one sales number.
So he's creating a continuous plot doing that.
Yeah. So he's just having a bunch of embeddings, and then he's concatenating, because this is because let me go back to this. What was this? This is the mixed input model. If you see here, these are the embeddings. These are the 22 embeddings. And then he has, what is it?
You'll get a better regression plot doing that.
Yeah, you'll get a better regression plot doing this stuff. Where is a simple linear model? Because he builds this model here. If you look at this, he says all these embeddings, he combines all these embeddings. He does, for I is equal to enumerate of all these embeddings, he does a loop over that, and then he concatenates it all into one long line, the embeddings. And then he does a dropout. I don't know why. I mean, these are the embeddings. If it's not 0, he does that. And then these are the continuous variables. He starts with the batch norm on the continuous variables. And then what he does is he concatenates these embedded variables with these continuous variables. So he does that if the self not embedding not 0, else x2. Okay. So he's just doing a long layer. He does all the embeddings, and then he attaches the continuous data points to it with the batch norm in front. And then after that, it's just he's putting ReLUs and other things after that. He's putting a linear layer. He's just zipping a linear layer drop, and then the batch norm into that. He just goes through. That's what we see.
Are they all linear?
They're all linear layers.
Everything?
Yeah, everything is linear layer. It's just some relus are there, which are non-linear layers because they do minus. It drops the minuses out. Otherwise, it's just branch norm and linear layers basically. And then at the end, you do a sigmoid on this.
Is this in lesson 3 and 4? Right?
Lesson 3 and 4.
Okay.
Yeah, sigmoid on this. So what I've done is in my lesson is just to, you have to dig through his code to see what model he's built. I've just shown you the model and stuff so you can see what the model is built. And if you see certain things you have to do, since you're building the model from scratch, you have to do all these, like you have to initialize with the scheming and stuff. We'll get into that. There are ways to initialize models, these layers, these linear layers and the batch norm layers and stuff like that. There are ways to see when in these linear layers, he's using a k-ming normal initialization. If you look at k-ming normal, PyTorch, k-ming normal is weight initialization. I mean, initialization example. It's one of those ways to weight initialize, but you don't even have to go to PyTorch. You can just say what is k-ming normal, and you will get that.
Yeah.
When to use residual network. He made normalization proper. I knew that made delving deep into rectifiers and stuff. I'll pull up some documentation on the k-ming normal and stuff. How do you start off with initial weights? It's because you are getting into stuff where now I have to set up the model from scratch because this is a model from scratch. And you have to initialize the variables and all that stuff. You don't need any initialization for embeddings and stuff. Those are kind of random things that will get done, but these linear layers, you have to initialize those things. Yeah, he just uses a bunch of linear layers and some dropouts and batch norms, and you get top 10 position on the competition, basically. Because if you do a random regressor, he shows that you won't achieve that kind of random forest regressor. You won't achieve anything close to that kind of accuracy what you get with the deep learning network. What you'll get with a random forest regressor is about 0.15, which won't place you much at all in your Kaggle competition there.
So should everybody watch like 3 and 4 then next time? Or?
Yeah, 3 and 4 you can start watching. I mean, if you finish 2, then you can start watching 3 and 4. He introduces the Rossmann and stuff in the 3 and 4. Yeah, it's way at the back of there because he's still talking 3. He's still talking about convolutions there.
But at least they can work through your notebook.
Yeah, work through my notebook to see how the deep learning, the setup and stuff. Then we can get into more details. I just wanted to at least introduce that and stuff because this is going to be very powerful. Tabular data set is everywhere. Time series data set is everywhere. Yeah. Okay, and if we can get a better model, his comparison is, if you see here, that's his comparison. I mean, you'll do that. Where does he do? Yeah, lesson 2, no. Fast AI. I thought I was in Fast AI.
So you're just importing prepped data from Tableau?
No, not importing. Oh, prepped data. Oh, what I did was I ran all the. Oh, you mean here when I said this?
Yeah.
The section 7, line 725. See here, I'm importing this join test, the prepped data. Yeah. Okay. Well, what I did was I ran his first half of the thing, and I prepped the data. Then I was experimenting with it. I didn't want to keep running this. I saved the prep data, and every time I just loaded the prep data, and that's all I do. So,
by any chance, would you know of a good place to kind of work and become proficient with use of Tableau?
Tableau?
Yes.
Oh, Tableau is different. Tableau is a visualization tool.
Well, I know.
Yeah.
Tableau is
Yeah,
a
I go by
tool I
default.
want in my toolkit
I know.
where,
I don't know where, I mean, you can go to videos and stuff.
okay,
Yeah.
yeah, I'll look at it.
Yeah.
I'm going to spend
Yeah. Alright, do you
the
wanna?
next 6, 8, 9 months amongst other stuff I'm doing, becoming much more proficient at this.
Okay.
I want to be able to pull things
Yeah.
from pandas from data streams, like say Kafka,
Yeah.
Spark.
Yeah.
Want to provide visualizations for all the things that
Okay.
I'm doing